Stars are large stellar bodies composed of gravitationally condensed hot gases, mainly hydrogen, and emitting electromagnetic radiation from gamma ray to radio frequencies because of nuclear reaction going deep in the core. Before the photographic study of stellar spectra, the scientists did not know the content of star-like sun. Lord Kelvin suggested that the large ball of interstellar gases shrink due to the inward pull of its own gravity. The gravitational energy converted into the thermal energy. Others suggested radioactive process going inside it. But if that would be the case, the sun perhaps exhausted within few years. In 1920, Arthur Eddington proposed that the sun may obtain their energy from the conversion of hydrogen to helium. It was Robert Atkinson who pointed out that the conversion may have related with the Einstein's mass energy theorem E = mc square. However, in 1939, Hans Bethe analyzed the different possibilities by which hydrogen fuses to helium. The first one was the proton-proton chain reaction, and the second was carbon-nitrogen-oxygen cycle. In 1954, Fred Hoyle describes advanced fusion stages like triple alpha process. That spectral analysis shows that the sun is made of 71% hydrogen and 24% helium, the rest other heavy elements. Theories of stellar evolution based on the studies of stellar spectra and their relationship with the luminosity and temperature. Generally, bright stars are hot, big, and have a shorter lifespan, whereas the smaller stars are cool, faint, have a larger lifespan. Once large gas balls accumulate a certain mass limit, their core became hot and dense enough to ignite hydrogen to fuse helium in their core, releasing tremendous amount of energy. Such stars are in hydrostatic balance between inward gravitational push and outward nuclear pressure. Such stars are called main sequence stars. Now let's talk about the mechanism of star formation. A star begins its life as a large dense core of cloud and a very cold. Temperature lies between -200 to 10 degree Kelvin, and they are observed by large infrared telescopes. These clouds are called giant molecular clouds. Typically, giant molecular clouds are roughly 100 to 200 light years across and may contain 6 to 10 billion solar masses. Generally, the formation takes place because of gravitational condensation, collision between large clouds at a very high velocity, supernova explosion, and radiation pressure. The pre-main sequence star shrink under the gravitational force. As the star shrink, gravitational energy converted into heat. As the center of the star compresses rapidly, the gradients of its pressure, density, and temperature increases. Just before reaching the main sequence, the star became hot spherical object surrounded by gaseous cloud. The star at this stage is known as T Tauri stars. The fate of stars mainly depends upon its initial mass of the protostar. When the mass of the protostar lies between 13th to 80 Jupiter masses, its inner temperature, core temperature, rises to 1,000,000 degree Kelvin, and at this 1,000,000 degree Kelvin, deuterium starts burning. The deuterium reserve finishes within million years. This non-luminous substellar object are known as brown dwarf. However, this brown dwarf does not fall in the category of main sequence stars. The least possible initial mass that can be considered as a main sequence star are called the red dwarf. When the initial mass of a protostar is less than 0.5 solar mass, the hydrogen converted into helium. The heavier helium dropped in the central core, pushing the hydrogen outward. The helium core formed in the surrounding cells. This process continues for billions of years. The red dwarf are the coolest main sequence stars, and the lifespan is about 10 to 30 billion years. The ultimate fate of stars depends upon its initial mass of its protostar. If the initial mass of the star greater than 0.5 solar mass but less than 8 solar mass, just like its previous case, the star burns hydrogen and having helium core. Due to the more masses, the gravitational pressure causes the helium core shrink further at the temperature of the core rises to 200 billion degrees Celsius, and this temperature is quite high for the helium flash. The shell of the helium fusion star outside the core surrounding by the cell of hydrogen fusion. This new output energy causes the outer layer to expand until its diameter expands to 100 to 200 times its present value. Our old sun is also expected to have this fate, and its diameter will be such big that it will engulf our poor Earth and may cross Mars. 100 million years after the red giant phase, when all its energy will used up, the exhausted red giant will put off its outer layer with an explosion, leaving behind a hot core. The temperature of this hot core will be about 50,000 degrees Celsius, and its outer layer boiling with fast wind traveling with 6 million miles per hour. As the fast wind moves, the slowly moving core creates a disc-like filament, appears as a disk of a planet. So it's called a planetary nebula. However, it should be noted that there is no relation with any planetary system. After a million years, the planetary nebula collapsed to form a white dwarf. Till this process, the star loses almost 30 to 40% of its initial mass. During its red giant stage, many stars, its density, surface area, and so as the luminosity oscillate periodically, and therefore such stars are also called variable stars. The diameter of the white dwarf may lies between 400 km to 4000 km, and its density may be 10 to the power 5 to 10 to the power 8 gram per centimeter cube. Let's move to the next case, when the initial mass of the protostar greater than the 8 solar mass but less than 25 solar mass. Then just after the finishing of hydrogen, the helium starts burning and produces carbon. When the helium finishes, the star again starts contracting, and this again causes increase in temperature up to 600 million degrees, and carbon-nitrogen-oxygen cycle starts, leaving a thick shell of remaining helium outside. Completion of sufficient carbon ceases the CNO process, and again the contraction followed by increase of temperature up to 1.5 billion degree Kelvin, which causes to burn oxygen and carbon to give neon, magnesium, sulfur, silicon, and lastly silicon converted into iron at 3 billion degrees Celsius. The above process completed formation of elements of one after another up to iron, leaving a patch of shell of every stage of element, just like an onion shell. The iron core at this stage was at highly compact degenerated state. Further cease of nuclear reaction causes to rush the gases to superfluid iron core, but as the masses were not enough to compress the iron nucleus, and also heat generated were not enough to start nuclear reaction of iron, within 1/10 of the second, a catastrophic explosion occurred, and all except the central part of star blown away at a speed excess of 50 million km per hour. A thermonuclear shockwave races through, and now expanding stellar debris fusing higher elements to heavier one and producing a brilliant visual outburst that can be intense as the light of 10 billion suns. Such phenomenon is called supernova explosion, and after such explosion, a tiny central part of star left behind, and the matter thrown off its explosion are called supernova remnant. The central core of the star which is left behind is called neutron stars. Typically, neutron stars are 20 km across and contain more masses than Sun and density of 10 to the power 14 gram per centimeter cube. Magnetic field around the neutron star are very strong. If the neutron star rotating very rapidly, as most of the neutron stars do, the strong magnetic field combines with the rapid rotation produces an electrical potential difference of trillions of volt, and this causes radiation of high energy particle and radiation of radio wave X-ray to gamma ray. The magnetic field of neutron star funnels the matter towards its magnetic pole. As the neutron star rotates, the hot matter concentrates out to produce X-ray pulses, and these X-ray producing neutron stars are called pulsars. What is the ultimate fate of the star having masses more than 25 solar mass? The gases goes on collapsing in the center because of the tremendous gravity and the amount of heat generated in this process not enough to halt the collapse. In other words, the gravity overcomes the outward exclusive pressure. As the star contracts, the gravitational field at its surfaces gets stronger and stronger. Due to the large concentration of mass, the central gravity so much increases that the whole star shrinks to a very small region, theoretically sometimes called a point of singularity. According to general relativity, the presence of mass affects the very geometry of space-time, and geometry of space-time in turn tells the mass how to move. So the gravity is nothing but the bending of space-time curvature towards the mass. If the mass goes continuously increasing to a point that causes high depression of space-time, and thus even light bends inward so much that it cannot escape. According to special relativity, nothing can travel faster than light. So if light cannot escape, neither can anything. This region is called black hole. Although a black hole have no surface in usual sense, there is a simple region or a boundary in space-time around a black hole beyond which we cannot see, as even photon particles dragged within it, and such boundary are called event horizon.